Welcome to the Deep Dive. Today we're plunging into one of the most profound and, well, frankly, vexing questions in modern physics. It's a question Eric Weinstein, a thinker as brilliant as he is controversial, sort of encapsulates with this simple haunting phrase. What is the fire that lights itself? To really get the weight of that, you might picture M.C. Escher's lithograph, drawing hands.
Oh, yeah, the two hands drawing each other.
Exactly. They seem to emerge from the paper, somehow bringing each other into existence. It's just this powerful visual metaphor for the ultimate challenge in fundamental science. How do you build a theory that's so complete, so self-contained, that it doesn't, presuppose its own foundation?
Right. In the Escher drawing, the paper is it's just there. It's a given.
Yeah, but for a true theory of everything, the theory itself has to somehow, well, Weinstein says it has to will the ink into being, has to create its own groundwork, its own rules from almost nothing.
That's a very high bar.
It is. And that is our mission today. We're embarking on a deep dive into Eric Weinstein's highly ambitious and, yes, highly controversial theory, geometric unity, often just called GU. We're going to try to break down its core scientific concepts, the geometry, the higher dimensions, the really remarkable derivations it claims to make about our universe.
That's not just the science, is it?
No, definitely not. To really understand why such a huge theoretical effort making these profound claims has largely, existed outside the usual scientific channels, we also have to navigate the very personal, often quite combative story of its creator. Our sources for this deep dive are Weinstein's own public lectures, his detailed explanations, plus various discussions and interviews where he really gets into the theory and its context.
Okay. And to really appreciate what geometric unity is trying to do, we first need to set the stage, understand the crisis it's trying to resolve. Because fundamental physics, as a field, it's experienced something, well, mysterious. A really abrupt stagnation.
Stagnation. That sounds serious.
It is. This intellectual slowdown really kicked in around 1973. That's roughly when the standard model of particle physics, our basic understanding of particles and forces, was intellectually solidified. It was a huge triumph, obviously.
Right. Unifying three of the four forces classifying particles.
Exactly. Electromagnetism, the strong nuclear force, the weak nuclear force, all wrapped up. But here's the striking thing, and it's something Weinstein and others find deeply, deeply unsettling. If you look at Nobel Prizes for fundamental theory in physics, specifically the ones for really profound new theoretical contributions to how we understand the universe at its most basic, you notice something odd. No one born after 1951, and someone like Frank Wilczek is a key example here, no one born after 51 has received a Nobel for a clear and profound contribution to fundamental physics theory.
Wow, that's barely 50 years.
Almost 50 years. And we're not talking about just a slow patch. This is a widely acknowledged long-term drought, right at the core of theoretical physics. And it's something that many people, Weinstein included, argue demands not just new ideas, but radically different thinking, completely different approaches.
So this long stagnation, this lack of breakthrough.
It leads us right to what geometric unity calls the twin origins problem.
Okay, the twin origins problem. Let's get into that. Eric Weinstein, for those who might not know his work super well, he's this brilliant mathematician and economist, too, known for really sharp critiques, often unconventional, definitely iconoclastic views.
An outsider in physics, though.
Definitely an acknowledged outsider in academic physics.
Yeah.
And the huge question he makes us confront, the one he spent decades on, is why has fundamental physics been stalled for almost 50 years? And his answer, well, it's pretty radical. He basically says, what got you here cannot get you there.
Meaning the current tools are insufficient.
Exactly. He fundamentally believes the current tools, the established structures, even what he calls the political economy of science itself, they're just not enough for this final, crucial leg of theoretical discovery. He argues pretty forcefully that we've effectively starved our scientific enterprise for resources, which created this dire and cutthroat competition that, in his view, has completely deranged the scientific tradition.
That's strong language.
It is. He thinks the career structure, the journal system, the whole academic employment setup, it cannot possibly complete the job of finding a theory of everything. It actively discourages it, he thinks.
Right. And this twin origins problem that GU is built to solve really speaks to that foundational impasse, that half-century stall. At its core, it points out what Weinstein sees as this fundamental mathematical incompatibility, almost a deep philosophical clash, really, between the two huge pillars of modern physics, general relativity and the standard model.
Okay, GR and the standard model pillars, but incompatible.
In a crucial mathematical sense, yes. So on one side, you have general relativity, G.R. Einstein's masterpiece. It's built on what we call intrinsic geometry, specifically Riemannian geometry.
Space-time is a curved fabric.
Exactly. Space-time isn't just a background stage. It's dynamic, it's curved, and gravity is that curvature. Think of the bowling ball on the rubber sheet analogy. The dip is gravity's effect. And Einstein's method involved this mathematical operation called contraction. He took the Riemann curvature tensor, which is a really complex object describing all the curvature at a point, how it bends, twists, stretches.
Right, very complex.
And he contracted it down to the Ricci scalar. That specific part measures how volume changes in curved spacetime. And that Ricci scalar directly connected the geometry to gravity in his field equations. It's geometry literally becoming gravity.
Okay, that's GR. What about the standard model?
So the standard model describes everything else, all the particles, the other three forces. But it's built on a completely different mathematical foundation, auxiliary geometry. Or you might hear it called fiber bundle theory, Ariasmanian geometry, modern gauge theory.
Auxiliary geometry, so not intrinsic to space-time itself.
Right. It deals with particles and forces by assigning these internal quantum numbers, like electric charge or the color charge for quarks. Think of them like labels attached at each point in spacetime, but they aren't properties of spacetime. They're free to choose.
Like choosing a different color thread at each stitch.
That's a good way to put it. Now, the incompatibility comes in how these two frameworks clash mathematically. GR naturally uses things like the Levi-Civita connection, which tells you how to parallel transport vectors in curved space and these geometrical contractions. But those very operations, they're not naturally allowed, not even really interpretable within the gauge theory framework of the standard model.
So they speak different mathematical languages.
Fundamentally different. Let me give you a concrete example Weinstein often uses. Einstein's famous contraction, taking the full Riemann curvature, which is a two-form, valued in the two forms, and simplifying it to the Ricci tensor.
Okay.
That specific operation, Weinstein says, is not allowed in the Ariasmanian world of gauge theory.
Why not?
Because in gauge theory, if you have two mathematical objects, like two forms, they are generally subject to independent gauge rotations or transformations. But Einstein's contraction treats one of those two forms as fixed to the manifold, while the other is allowed to transform.
Ah, so it breaks the rules of gauge theory.
It treats them differently, yes.
Yeah.
It creates what Weinstein calls this unacknowledged battle between Charles Ariasman and Bernard Riemann, representing these distinct mathematical traditions. He also dismisses what he calls a fake meme in physics, the idea that the diffeomorphism group of GR, which deals with smooth spacetime deformations, is just like the gauge group of the standard model. GU insists, no, that's not true gauge theory. They're different, and trying to force them together is the root of the problem.
Okay. So incompatible frameworks. What else? You mentioned torsion earlier.
Right. In differential geometry, you usually have this sort of triumvirate of tensors describing geometry. The metric, distances, angles, Riemann curvature, bending, and torsion, twisting. But in standard theories, GR and the standard model included, torsion, even though you can define it, is almost always just set to zero. Ignored. Weinstein calls it the weak sister.
But GU wants to bring it back.
Definitely. GU seeks to rescue its role, give it a central, crucial part to play. And this all feeds back into Einstein's philosophical question, whether the creator had any choice in how the world was constructed.
The fire that lights itself.
Exactly. Weinstein takes that not just as philosophy, but as a research program. How do you get a theory of everything? Not one that predicts every outcome, but one that explains how does one get everything from almost nothing? A theory where the paper is presupposed, but the theory itself must somehow will the ink into being. It must create its own foundation.
Okay, so that's the massive problem GU is trying to tackle.
Yeah.
This deep incompatibility, this stagnation. What's the core idea, the proposed solution?
The foundational move is radical. Instead of trying to quantize gravity on our usual 4D spacetime, let's call it X4GU, shifts the whole arena of physics. It says the true stage isn't X4, but a much larger 14-dimensional space called the Observerse, or Y14.
14 dimensions. Okay, where did the extra 10 come from?
Good question. Imagine every single point in our normal 4D spacetime, X4. At each point, you can define a metric, the rule for measuring distances and angles right there.
Right.
In 4 dimensions, that metric needs 10 independent numbers to fully describe it. Think of it as 10 ways space can locally stretch or shear at that
These
point.
10 numbers per point. Okay.
Now, instead of choosing one fixed metric like GR does, GU considers the space of all possible metrics at each point simultaneously.
All possible geometries at once.
Point-wise, yes. So you take those 10 components defining the local metric and you add them to the original 4 dimensions of spacetime itself. 10 plus 4 gives you 14. Ah, okay. So the Observerse Y14 contains our spacetime X4 plus all the possible ways spacetime could be curved at each point.
Precisely.
Ugh.
You're working in this grander space where every potential local geometry is part of the fundamental reality.
That's a lot to take in. Is there an analogy to help visualize it?
Weinstein uses the analogy of a stadium. Think of our familiar 4D spacetime X4 as just the playing field.
Where we see the action happen.
Right. But the 14D Observerse Y14 is the entire stadium, the stands plus the pitch. The fundamental fields, the real stuff of reality, they dance on Y, meaning their true dynamics happen in this 14D space.
But we only see the field.
We observe them via pullback as if they lived on X. What we see as physics in our 4D world, particles, forces, gravity, is actually a projection, like a shadow of deeper dynamics happening in the Observerse.
Like watching shadows on Plato's cave wall, maybe?
Kind of, yeah. Seeing a lower dimensional representation of a higher dimensional reality. So, okay, if I'm getting this, instead of one fixed reality, we're looking at a fundamental space encompassing all potential realities, or at least all potential local geometries, simultaneously. That's a huge shift. How does working with this whole space of possibilities, this Observerse, actually help solve those big problems?
Yeah.
What's the magic trick here?
Right, that's the key question. The answer lies in something GU calls this chimeric bundle, and its crucial role is in defining matter itself.
Matter, like electrons and quarks.
Exactly. The fundamental objects describing matter are called spinors. Now, here's the paradox traditional physics hits. To define a spinor, usually you need a pre-existing metric. You need to know the geometry of space-time first.
Okay, makes sense.
But in quantum gravity, where gravity itself is quantized, the metric isn't fixed. It's supposed to be fluctuating, fuzzy, uncertain.
Ah, the chicken and egg problem.
Precisely. How can matter exist? How can you define its properties if the space-time metric it lives in isn't well defined? It's a fundamental circularity.
So how does the chimeric bundle fix this?
It's a really novel mathematical construction built over the Observerse, Y14. Think of it as combining 2 key geometric pieces. There's the vertical bundle, which represents changes in the metric at a specific point, all the ways the local geometry can vary there. And there's the dual of the horizontal bundle, representing movement in the base spacetime X4.
Vertical for metric changes, horizontal for space-time movement. Got it.
Now, the vertical part naturally gets a metric signature of 4.6, 4 plus signs, 6 minus signs. The horizontal part, our spacetime, is usually 1 or 18.3. When you combine these in the chimeric bundle, the whole structure ends up with a signature of 7 on 7.
7 plus 7 minus. Okay. Why is that important?
Here's the breakthrough. Because this chimeric bundle is constructed in a very clever way, it's mathematically equivalent, or isomorphic, to both the tangent and cotangent bundles of the whole Observerse Y14 it allows. Get this. Spinors to be defined before a metric is chosen.
Whoa. So matter can exist before the geometry is fixed.
Exactly. Spinor bundles, the mathematical homes for matter particles, can exist intrinsically within this higher dimensional Observerse without needing a prefixed metric or connection. It just completely bypasses that chicken and egg problem.
That's genuinely clever. It gives matter a foundation even when gravity is quantum.
Right. And that 7-7 signature, it's not random. It naturally gives rise to the spin 7 group as its fundamental symmetry group.
Spin 7.
And this group is crucial because its spinor representations, the ways it can describe particles, are uniquely able to hold both gauge fields, forces, and fermions, matter, within a single unified framework.
Ah, so the unification starts right there in the symmetry group.
It's the first big hint that everything might genuinely emerge from this geometry.
You also mentioned a Zorro construction.
Ah, yes. That's Eric's specific technique for connecting our 4D base space, X4, to this bigger metric bundle, Y14. Think of it as a standardized way to lift information from our spacetime up into the Observerse and induce the right mathematical structures, the connections, up there. It links the 2 worlds.
Okay. And there was one more piece. IgGY.
Right, the inhomogeneous gauge group, IgGY. It sounds complicated, and it is. It's a semi-direct product structure. It combines the usual gauge transformations physicists use for forces with something called affine translations on the space of connections.
Meaning.
Essentially, it gives you two distinct ways to act on the connections describing forces.
Hmm.
This very complex group structure is absolutely vital for how the fields in GU transform, interact, and ultimately unify. It shows the depth of the mathematical structure being built here.
Okay. So we've got this incredibly complex 14-dimensional observers, the
Yeah.
chimeric bundle, solving the spinor problem, spin 7-7 symmetry, hinting at unification. It's a lot of abstract geometry, a lot of intricate
Yeah.
math. But now the really crucial question for, for us trying to understand this, what do we actually get out of it? What falls out of this geometry when you pull it back to our familiar 4D world? Does it actually predict the universe we see?
That is indeed the ultimate test. And this is where GU makes its most profound claims. It asserts that much of the universe's structure emerges naturally, necessarily, from this geometry, not put in by hand.
Like what, for instance?
One of the most striking claims is deriving the three generations of matter. You know, the families of quarks and leptons.
Up-down electron, charm-strange muon, top-bottom tau. Those three families.
Exactly. GU predicts a specific 2+1 model for matter. 2 true generations and 1 imposter generation.
The imposter, why?
We'll get to that. But the point is, this 2+1 structure isn't just assumed. It arises directly from studying a mathematical object called the Dirac-Rorita-Schwinger complex, but studied on the 14D Observerse Y14. And remarkably, this complex, within the GU framework, naturally breaks down into 3 distinct sets of fermions. Exactly 3.
Wow. How does that breakdown work?
Well, mathematically, there's a scalar spinor part that gives you the first generation. Then there's a vector spinor part, which splits again into 2 pieces, a gamma trace part for the second generation and a gamma traceless part for the third.
And these match the particles we see.
Each component is 16-dimensional, perfectly matching the fermion structure within each generation of the standard model. And the imposter label for the third generation comes from how it behaves at very high energies. Unlike the first 2 generations, which would just unify onto themselves, the third generation, GU predicts, would reunify with other currently disconnected predicted particles. It looks the same now, but its high-energy origin is different.
That's fascinating. And what about things like chirality, the left-handedness of weak interactions?
GU suggests chirality isn't put in initially either. It's an emergent property arising naturally from the mathematics of this complex. It's tied to this exponential property of spinors and a slightly more complex role for the Rorita-Schwinger part that singles out that third generation. So it's not just fitting data, it's claiming a geometric reason for the 3 generations.
Okay, 3 generations of matter. What about forces? The Higgs boson.
Right. GU claims these also emerge intrinsically. They are not added in separately. The Higgs field, Yang-Mills fields for the other forces. They are all components of a single unified gauge potential that exists naturally on the Observerse, Y14.
So the Higgs isn't bolted on.
No. Weinstein says it lurks within the variational part of the gauge potential on Y14. When you decompose this potential, the part related to vertical fluctuations, think ripples in the metric dimensions. These yield symmetric 2 tensors on our 4D spacetime X4. And these symmetric tensors naturally split into a trace part and a traceless part. This mathematically mirrors the relationship between the spin 0 Higgs and the spin 2 graviton.
Implying a unified origin.
Exactly. A unified origin for Higgs and the Yang-Mills forces. And the same mathematical contraction mechanism, the one related to the Shayab operator we'll mention later when applied to these vertical fluctuations, naturally produces the kinetic and potential terms for the Higgs. It gives you the right kind of equation, the Klein-Gordon equation, with that characteristic quartic self-interaction.
So the Higgs mechanism itself falls out of the geometry.
That's the claim. It emerges, it's not imposed.
Okay, what about the standard model symmetries themselves? The SU3 x SU2 on G1.
Again, the claim is necessity, not choice. This exact group structure appears as a necessary consequence of the geometry. It emerges as what's called a maximal compact subgroup of that larger spin 7-7 symmetry of the Observerse.
Maximal compact subgroup,
Right.
meaning the biggest well-behaved chunk of the larger symmetry.
Essentially, yes. It's a natural, stable subset. The reduction goes like this. Spin 7-7 breaks down first to spin, the tension 7, that's space-time Lorentz symmetry, special relativity times spin 4.
Okay.
That remaining spin, 6 opposed 4, acts on the 10D metric fluctuation space. It further reduces to spin 6 times spin 4, and now, due to some well-known mathematical equivalences, spin 6 is the same as SU4, and spin 4 is 2 copies of SU2. This naturally leads to SU4 x SU2 x SU.
Which is the Patti-Salam group, a known GUT candidate.
Exactly, a well-respected grand unified theory group. And from there, standard particle physics techniques, what Weinstein calls GUT folklore, reduce this Patti-Salam group down to the standard models SU3, XU2, XU1. It all flows from spin 7, 7.
So the claim is the entire standard model structure is basically baked into the geometry of this 14D Observerse.
That's the core assertion.
What about the biggest elephant in the room, the cosmological constant, lambda, that 120 orders of magnitude problem?
Right, the greatest problem in physics. G offers a really radical reinterpretation here. Instead of being a static constant that needs unbelievable fine-tuning, GU predicts lambda as a field.
A field, not a constant.
Yes, a dynamic field derived from the geometry. Specifically, it's identified with a parameterized torsion.
Torsion, so this lambda field can change.
It's free to respond to the curvature in the vacuum. The idea is that the scalar curvature of the observers can coax this torsion field out of the vacuum, effectively allowing spacetime to dynamically generate the cosmological constant's value, resolving the fine-tuning nightmare.
How does torsion enable that? I thought it was the weak sister.
Weinstein argues physics has been using slightly the wrong notion of torsion. He redefines it just a little adjustment, he says, as the difference between any connection and the gauge-transformed Levi-Civita connection, the GR one. With this redefinition, called the augmented torsion tensor, torsion becomes your best friend. It's a dynamic field, crucial for consistency and solving the lambda problem.
Okay. And making all this work required new math tools.
Yes, absolutely central are two inventions by Weinstein, the Chiab operator and this augmented torsion tensor.
The Chiab operator, what does that do?
It replaces Einstein's naive metric contraction, which, remember, had issues with gauge theory. The Chiab operator is a sophisticated gauge covariant map. It processes the full curvature on Y14 and outputs a symmetric 2 tensor. This recovers a gauge covariant version of Einstein's G tensor plus a cosmological term, which is then equated to a derived stress-energy tensor. It replaces the Einstein equations with something like swervature equals dysplasia, gauge invariant curvature equals a measure of distortion involving this new torsion.
So these tools, Chiab and augmented torsion, are essential for making the geometry yield physics and fixing the gauge issues.
They are the key mathematical machinery invented within GU to bridge that gap between GR and gauge theory, enabling all these derivations. It's an attempt to answer Einstein's question about choice, aligning with Dirac's idea that the fundamental laws should yield the consequences naturally.
It's an extraordinary picture. Deriving matter, forces, symmetries, even tackling lambda, all from geometry. But, and it's a big but, for such a potentially revolutionary idea, it exists so far outside the mainstream. To really get why, we have to dig into the human factor, the story of Eric Weinstein himself.
Right, the context is inseparable from the content here.
Absolutely.
Yeah.
He has this long-standing, deeply felt narrative of being an outsider in academic physics. He doesn't just distrust the system, he seems to view it as fundamentally broken. He talks about the political economy of science having starved our scientific enterprise, leading to dire and cutthroat competition that's completely deranged the scientific tradition.
He connects this directly to the stagnation we talked about earlier.
He does. He believes the career structures, the journals, the funding it all makes pursuing truly fundamental long-shot theories almost impossible. He calls it career suicide. And he thinks this systemic failure explains the 50-year synchronous failure in fundamental theory. He's also very critical of string theory's dominance. He feels it became entrenched with the baby boom generation of physicists, partly because it allowed for infinite elaboration within a mathematical work, especially geometrically.
Meaning people could work on the math without necessarily connecting back to testable physics.
That's his claim. He argues many papers on the HEP, the preprint archive, are about very strange and obscure mathematical issues, pulling talent away from core questions about particles and forces. And his response was to basically opt out of that system. Largely, yes. He talks about pursuing an H-index of 0, deliberately avoiding traditional publication metrics. He sees peer review, often not as quality control, but as peer injunction, a way to block or co-opt new ideas.
Peer injunction, that's a striking phrase.
It is. He really dislikes the debunking community, seeing it as just background chatter of laughing at people, creating a terrible and combative environment that kills many of our best ideas. He says, great science has the scientific method as its radio edit. The real process is much messier, much less sanitized than the official story.
Hmm. And central to this whole narrative is the Seiberg-Witten story, isn't it?
Absolutely crucial. He presents this narrative that a flake, his word, a piece of geometric unity's mathematical structure, was independently rediscovered around 1987 at Harvard. This became known as the Seiberg-Witten equations. Weinstein claims he was working on these ideas, the precursors, years earlier.
And his claim is he received no credit.
Zero credit is how he puts it. He recalls presenting related work but being told it was insufficiently nonlinear, or that his Einsteinian interpretation, first-order incurvature, was misunderstood as just Yang-Millsian. He believes they missed the deeper geometric point he was making. He wasn't even allowed to speak at a Princeton conference about these new equations.
That must have been incredibly frustrating.
He says it was really dramatic, and it solidified his decision to develop the rest of GU in almost total isolation for decades, working completely on your own, building from decades of notes, not expecting to talk to anyone.
Which has its own challenges, surely.
He admits that, occasionally getting turned around, forgetting details of his own intricate work. But importantly, he explicitly says he does not think Witten or Seiberg took the ideas from him directly.
So it's not an accusation of plagiarism?
No. He acknowledges Witten's brilliance, suggests Seiberg maybe didn't initially grasp the full significance. His issue is with the system, the academic culture that, in his view, fails to recognize or credit independent discovery, especially from outsiders.
A systemic failure, not necessarily individual malice.
That seems to be his main point. And his critiques extend more broadly. He calls figures like Lenny Susskind malign influences, who throw fear, uncertainty, and doubt at anyone not towing the party line, which he sees as string theory. He thinks the field is operating in a circular fashion, calling the establishment the blue hair problem of physics for making one theory the only game in town.
It's a very pointed, very personal critique of the entire culture.
Deeply personal, yes.
Okay, so let's try to summarize the technical side, the core merits GU claims. It really does propose this novel, quite elegant solution to that paradox. Defining matter, spinors, without needing a fixed metric first. That's achieved by moving to the 14D Observerse and using the chimeric bundle. It's a fundamental shift.
Right, solving the chicken and egg problem.
Exactly. And then it offers this profound geometric origin for the standard model structure. The SU3, XSU2, 1 symmetries aren't just put in. They emerge as a maximal compact subgroup of spin, 7,7. The Higgs field isn't added. It emerges from the gauge potential on the Observerse. The 3 generations of matter, including the imposter, are derived from the Dirac-Ria-Schwinger complex on Y14.
And the cosmological constant solution via torsion.
And the dynamic cosmological field from parameterized torsion, plus that re-envisioned role for torsion using the augmented torsion tensor, all made possible by those key tools invented within GU, the Shiab operator, and the augmented torsion, which tackle that core gauge incompatibility. It really tries to fulfill Dirac's idea that a fundamental theory should naturally yield the observed universe, not just accommodate it.
So we have this theory with these immense claims seemingly tying up loose ends, deriving fundamental structures from geometry. And then we have the narrative. Is this a lone genius battling a flawed system that suppresses innovation and misallocates credit, the outsider fighting the establishment? Or is it a cautionary tale about the potential downsides of extreme intellectual isolation? Does working outside the collaborative, critical environment of peer review perhaps hinder the refinement, the error checking, needed for such a complex theory to gain acceptance, even if it has merit?
It's the central tension, isn't it?
It really is.
Yeah.
Weinstein himself uses this fool's gold analogy. He frames his life's work, this massive investment of time and intellect, as taking my shot on goal. He acknowledges the risk, saying even if it's wrong, maybe it gives physics something to go on.
A pointer, even if not the final answer.
Exactly. So the question remains, is this shot on goal the real thing the unified theory physicists have dreamed of? Or is it compelling, intricate, but ultimately fool's gold? Perhaps incredibly valuable fool's gold that points the way, but not the destination itself.
We don't know yet.
We don't. But whether geometric unity ultimately proves right or wrong, Eric Weinstein's 40-year journey absolutely forces us to ask these really uncomfortable, really important questions about how science gets done. Who gets to participate? How do we evaluate radical ideas from outside the mainstream? And how do we make sure we don't stifle the kind of long-term, potentially solitary, high-risk thinking that might be needed for the next true revolution? Especially now in an era where many feel fundamental physics has stagnated. How do we balance rigorous peer review and collaboration with the need to nurture those potentially paradigm-shifting but maybe unconventional ideas? That's the provocative thought we leave you with. This is Ben Carter.